Welcome back to the Machine Learning 101 course. Today we will learn about some of the common techniques used to select the right machine learning model and how to tune a machine learning model for superior performance. But first, let's start with a quick recap. So far, we learned about various supervised learning algorithms that can be used for regression and classification problems. In the last lesson, we looked at decision trees, which are a sequence of nested if-else conditions from the training data. After that, we looked at random forest models, which are an ensemble of decision trees and are very powerful for both classification and regression problems. We also looked at KNNs, which can make a future prediction based on the labels of the closest points in the training data. Though it is very simple and it does not involve any learning, it can still be a very effective model in many scenarios. There are many other models like naive Bayes, support vector machines, neural networks that we have not covered yet. Now, the obvious next question is, how do we decide which model to use and when? There's no one right answer to this question, as many of these models are very versatile, and often data preparation turns out to be the big differentiator as compared to model selection. Still, there are some general guidelines and process we can follow to find a better model. As we saw earlier, some models are more suited for regression problems, while others are better suited for classification. Training data can also influence model choice. For example, neural networks often are the model of choice when it comes to unstructured data. Also, if the number of features are in the hundreds, a more sophisticated model like random forest would be better than decision trees or logistic regression. And complex models like deep neural networks often require a lot of training data. Sometimes there's a trade-off between how well a model performs and how easy it is to explain the model's decision-making process. For example, simpler models like logistic regressions and decision trees are highly explainable, but often perform much worse than some opaque models like support vector machines and neural networks. Finally, of course, it all depends on the model's performance on that problem. And this is the part we will explore further in this lesson. But before that, let's understand what hyperparameters are, as improving model performance often includes hyperparameter tuning. The model training we have done so far is about parameter tuning. Example, we run the gradient descent algorithm to find W and B such that the cost function is minimized. This is called parameter tuning. Whereas hyperparameters are external model settings that are not learned from the training data. For example, how many trees we choose for a random forest, or the choice of k in k nearest neighbors. As these settings have a significant impact on the performance of the ML model, it is important to know the do's and don'ts when it comes to tuning hyperparameters. When training a model, we would like to make sure it learns properly. And therefore, when a model does not perform well on test data, we would like to analyze the mistakes it makes and update our training steps to help it learn better. And we will be tempted to do so repeatedly until we're satisfied by the model's performance on the test set. But this is a common beginner's mistake. Even if we don't use the test data as part of training, the approach might make the model overfit the test data, and its performance on future unseen data may be worse. So, if we cannot use the test data to analyze and improve the model, what do? A natural choice would be to divide the dataset into three parts: train, validation, and test. The validation set is used to analyze model performance and iterate. Only once we are satisfied with the model performance, we confirm if the performance holds for the test set as well. This is a reasonable approach and can be a good starting point. However, this approach also has some limitations. To be effective, the test and validation sets have to be large enough to be representative, which reduces the training data significantly. This can lead to a compromise in the model's performance. On the other hand, very small test and validation sets might lose their purpose if they're not able to represent the unseen data holistically. A common approach to work around this limitation is called k-fold cross-validation. First, we divide the training data into k folds. In this example, we're using k as 5. Then we let the model train using k minus 1. For example, 4 folds in this training data, and the 1 fold is used as the validation set. But we do not stop here. We pick a different fold as the validation set and train the model using the remaining k minus 1 folds as training data. This way, we end up with k trained models and a range of performance metrics on the k validation sets. We can analyze the errors across these sets, change our model settings, and run the entire process again until we're satisfied with the model's overall performance. Then we can use the best model settings to train a fresh model on the entire training data, all k folds, and evaluate its performance on the test data. Grid search cross-validation is a technique commonly used for hyperparameter tuning using k-fold cross-validation. As we discussed earlier, there are often many options for the hyperparameters, and it can be very tiring and time-consuming to try out every single option. Grid Search CV helps simplify this process. You can start by providing a list of hyperparameter options you want to explore. For example, in this code we have 4 different hyperparameters for random forest classifier, and each hyperparameter has either 3 or 4 possible options. The grid search will evaluate every single hyperparameter combination, which is 144 options. And let's say we pick k as 5 for cross-validation. The grid search CV will train 5 models for each of the 144 options, hence a total of 720 different random forest classifier models. This helps us find out what combination of hyperparameters gives best performance based on cross-validation sets and this hyperparameter combination. It can then be used to train model on the entire training set. This week's exercise looks at classifying a car as acceptable, unacceptable, good, or very good. This problem is tackled using 3 models: random forest, decision tree, and KNN, whose parameters are fine-tuned using Grid Search CV. To practice more with Grid Search CV, you can check out the problem posed by the problem.md file. The task is to judge the quality of wine between 0 and 10, based on the results of chemical analysis. You can try using Grid Search with classification and regression models for this problem. To learn more about hyperparameter tuning and cross-validation, check out these videos. There are also some tutorials on Kaggle for this topic. In the next lesson, we will go over unstructured data, like text, for a very common application, spam filters. They are also the basis of large language models, like ChatGPT.